All right, so today we want to go back and review factoring quadratics because we are going to be dealing with larger polynomials, and so factoring a larger polynomial we can't even do if we can't factor the quadratic polynomials. So we want to go back and review all of our methods for making sure that we factor quadratic polynomials correctly. So the first big thing is that making sure that we understand what a greatest common factor is. So a greatest common factor is shared by two or more numbers, monomials or polynomials. It means that it is a factor. A factor is something that divides something evenly. And if it's a common factor, it means it will divide all of them evenly. And if it's the greatest common factor, it means it's the largest factor that they all have in common. And so we want to make sure that we're always checking for the greatest common factor first, because all of our other factoring methods don't work if there's a greatest common factor in there. That greatest common factor in there messes up the other tricks we have for factoring and would show up twice, and therefore we'd get the wrong factors. So we always want to make sure that we take greatest common factors out first. So just a quick review, I want you to practice finding the greatest common factor. So when it's just a number, I want you to find the largest number that will divide both numbers evenly. Stop the video, pause the video, do that on your own first, and then I want you to check your answers. So hopefully you did stop and you found the GCF first on your own. Check your answers, make sure you got them right. A couple of things to make note of. Make sure that you notice that if both numbers are negative, you tend to want to make your greatest common factor negative as well. When it comes to looking for greatest common factors with polynomials, especially if the first term, the leading coefficient of the polynomial, is negative, you want to make your GCF negative. Because all of our factoring tricks that we know for factoring quadratics require the leading coefficient to be positive. So taking out a negative common factor is actually really important if that first term is negative. Also, don't forget that if two numbers seemingly don't have a common factor, all numbers have one common factor, and that is 1. 1 will divide everything. So it is the universal common factor, and sometimes we just need to take out the common factor of 1, or like I mentioned with the negative up here, sometimes we need to take out a negative 1 so that we can make that leading coefficient be positive. All right, so now I want you with variables and coefficients, finding the greatest common factor for variables. So with numbers, again, you're looking for the largest number that will go into all of the numbers. With variables, you're looking to see what variables do all of them have in common, and then what is the largest exponent, or the smallest exponent, excuse me. What is the smallest exponent on that common variable? So stop the video and try 1 through 6, and then you can check your answers. Again, I hope you stopped the video and actually figured these out. Again, what you're looking for is if they do have coefficients, deal with the number first, then deal with the variables. So find the number that will go into both of the numbers first, and then look at which variables do they both have, and what is the lowest exponent on that variable. So here they did both have an x and they both had a y, but the first power was the smallest exponent on both of those. Down here at 6, only one has an x, only one has a y. They don't have a common variable, and 4 and 5, their GCF is just 1. So sometimes, again, the GCF will just be 1. But always look to see if it has a greatest common factor. Now, the point of finding a greatest common factor is that we want to pull it out. We want to factor out the greatest common factor. And remember, when we talk about factoring out a monomial, we're basically talking about undistributing. We want to take that, it had originally been in front of the parentheses, and we want to pull it back out and put it back in front of the parentheses. So looking at these three terms, first thing I want to do is I want to find the GCF. So 15, 10, and 25, I believe 5 is the largest number that will divide all of those. They do all have an x, and they do all have a y. The smallest exponent on the x is 1, and the smallest exponent on the y is 1. So this is going to be our greatest common factor. What we want to remember is that factoring out a greatest common factor is undistributing it. So we want to move that up to the front, and we're basically going to divide it back out and move it back up to the front of the parentheses. So distributing, we take something that's being multiplied by parentheses and multiply it by everything inside of the parentheses. Factoring is undistributing, so we're going to divide everything by that common factor and put it back in front of the parentheses. This is again why we spent like a whole day reviewing just how to divide monomials, because that's what we spend the most time dividing. 15 divided by 5 is 3. X divided by x will just cancel, and y squared divided by y is just going to be y. Negative 10 divided by 5 is negative 2. X cubed divided by x will be x squared, and the y divided by the y will just cancel out. 25 divided by 5 is going to be 5. The x's are going to cancel out, and y cubed divided by y is going to be y squared. And so this would be factored because now they don't have anything in common. Everything they had in common has been brought out to the front. All right, so again, we always want to look for that GCF first. And guys, there's really multiple reasons that you always want to check for GCF first. Like I said, most of our factoring tricks don't work if there's a common factor, but you also want to take into account that if you take a greatest common factor out, the numbers you're going to be working with are going to be a lot smaller. And that makes working with them a lot easier. Finding numbers that multiply and add and all of our factoring tricks are much easier to do when we're dealing with small numbers, ones that don't have a lot of different factors. So finding greatest common factor also makes your work a lot easier. So looking at all of these, they're all even numbers. So they definitely all have a 2 in common. It does look like they all have an x in common, and the lowest exponent on x is 1. So that means that our GCF is going to be 2x, and we want to move that 2x back to the front. So we're going to undistribute it, factor out the 2x, and move it back up to the front. So now we're going to have a 2x at the front of our parenthesis, and 2 divided by 2 just cancels. X to the fourth divided by x to the first is going to be x to the third. Negative 8 divided by 2 is negative 4, and x cubed divided by x is going to be x squared. 4 divided by 2 is 2, x squared divided by x is just x, and negative 6 divided by 2 is negative 3, and the x's just cancel. And so this would be the factored form by taking that greatest common factor back out to the front. Now, remembering factoring quadratic trinomials. So quadratic trinomials, we got x squared, x, and a number. We're going to start, though, where a is equal to 1. So when there's just a 1 in front of the x squared, those are the easiest to factor. So remember, our trick for doing that is first we want to find all the numbers that multiply to equal 12. So pairs of numbers that multiply to equal 12. And it's positive 12. So 1 and 12, 2 and 6, 3 and 4. And we want to choose the pair that adds up to equal the b. So which of these actually adds up to equal 7? That's this pair. Now, don't forget the sign does matter. This was a positive 12. So that meant that these either both had to be positive or they both had to be negative. Since we wanted it to add up to equal a positive 7, I kept them positive. If this had been a negative 7, I would have made them both negative. And then those are the two numbers that end up going in our factors. Remember, a trinomial factors to be two binomials multiplied times each other. So this would be x plus 3 and x plus 4. And that's what would multiply. And you can check it. X times x is x squared. 4x plus 3x is 7x. And 3 times 4 is 12. So it does multiply back out if we do that double distribution or the box. And it gives us x plus 3 and x plus 4. Now, what happens if a is not equal to 1? It only changes up a little bit. The big thing to remember is that we have to take the a and multiply it times the c. I had a coworker that called that putting on the headphones. You have to make sure that you take that a and multiply it times that c and get 24. So 24 is the number that we want to find all the pairs of numbers that multiply to equal that. So we're still looking for two numbers that multiply to equal 24, but add to equal that b value. So we want it to multiply to be positive. So they're both positive or they're both negative. Since they're adding to equal positive, they must both be positive. So pairs of numbers for 24, 1 and 24, 2 and 12, 3 and 8, 4 and 6, and I think that's it. As far as the ones that actually add up to equal 14, I think that's 2 and 12. Because that's going to be the two that multiply to give me positive 24 and add to give me positive 14. So far, it's really identical to what we did when a was equal to 1, other than we had to remember to multiply by that a. And now we have our two pairs of numbers. This is the part where it does get a little different. So now that we know that the two numbers are 2 and 12, those are the two numbers that multiplied to give us 24, and they added to give us 14. What we want to do is we want to temporarily write that as x plus 2 times x plus 12. That's temporary, because I know that those two don't multiply to equal that, because 2 times 12 is 24, not 8. And x times x is x squared, not 3x squared. So I want to point out this is just a temporary step. Because what we're doing here is a time-saving trick. Mathematically, what we really should do is go back to the box, and now we know what those two corner boxes were that got added together to give us 14x, and then we can pull out that common factor. The problem is we're going to be using factoring so much moving forward, we don't have time to do that whole box thing. And so we want to have a more efficient way that we can get to the correct factor. So once I know these two numbers, I just go ahead and write them as factors, but I want to go back and remember this number from up front. And so I'm just going to take that leading coefficient, and I'm going to divide those two numbers by it. Now, what I'm really doing is figuring out where that 3 went from. Sometimes these numbers don't divide. And so whenever they don't divide, and I get this fraction, what that means I want to do is that number must have originally been up here. So that would be 3x plus 2. Now 12, if it does divide, sometimes it does divide. And so whatever that turns out to be, this is just x plus 4. So that's where that 3 came from. And so here it didn't divide, so it moved up to the front. Here it did divide, so it just stayed 4. Notice 3x times x is 3x squared. 2 times 4 is 8. We get 12x and 2x, which gives us the 14x. And so this is the factored form of that. So I want you to pause the video, and you're going to factor all of these, and then you're going to check your answers. So pause your video now. All right, now you can check your answers and make sure that you did factor these correctly. Again, make sure your variables don't magically change. This was t, so it needed to stay t. Down here at the bottom, 2 times negative 21 was negative 42, so two numbers that multiplied to give me negative 42 and added to give me positive 1. So I did x plus 7 and x minus 6, but I had to remember to divide them by 2, so I got 2x plus 7 and x minus 3. For number 6, 3 times 10 is 30. Two numbers that multiply to equal 30 and add to equal 11 were 6 and 5. So x plus 6 and x plus 5 divided by the 3 ended up with x plus 2 and 3x plus 5. Now, we do have a couple of special cases that we want to remember, and we want to be able to notice them on sight. If I have a binomial, remember that means two terms, and it's a perfect square minus a perfect square. Those are always going to factor. A perfect square minus a perfect square actually factors to be what we call conjugate pairs. They factor to be conjugate pairs. And that means that they have the same two values, but one of them we're adding those two values and one of them we're subtracting those two values. And the reason this always turns out to be that binomial squared is because a times a is going to be a perfect square, and b times negative b is going to be negative b squared. Here we get negative ab, and here we get positive ab. Those two middle terms always cancel out. They add to equal 0. So this is called a conjugate pair. There's a vocabulary word for you. And that's what we get when we factor a perfect square minus a perfect square. Big notes to make to yourself. Must be minus. It doesn't work if it's a sum. If it is addition, doesn't work. Doesn't factor. It's prime. But if it's subtraction, and they're both perfect squares, then it will factor. And so it is important that they must be subtracted from one another, and they must be perfect squares, which means you really need to be able to identify and recognize those numbers that are perfect squares. So it is my strong recommendation that you have at least memorized what the first 15 perfect squares are. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. Those are the first 15 perfect squares. Because if you see those numbers popping up in your binomial, and you see variables that are squared, and you see a minus sign, then you really want to factor that as a difference of two squares. So let's look at an example. Okay, so if I have x squared minus 4, again, first thing that pops into my head is, oh, that's a perfect square because it's x squared. And oh, 4 is on my list. It's 2 squared. So this is a perfect square minus a perfect square. I know my answer is going to be a binomial times a binomial. So I'm going to write down my binomials. I need to know what the square root of each of those are. What squared equals x squared? It's x squared. And what squared equals 4? 4 is 2 squared. So when I take the square root, I want to put them in both my binomials. So I have x and 2 and x and 2. And then I'm going to make one of them plus, and I'm going to make one of them minus. And that gives me my conjugate pair that this factors to be. and that's factored. Now, again, knowing your perfect square numbers, 9 is a perfect square. It's 3 squared. And 25 is a perfect square. It's 5 squared. My variable is x to the 4th. So I have to think about that for a second, because that's not x squared, but it's an even power. All even powers are perfect squares. X to the 4th is x squared times x squared. So that's taking something and multiplying it times itself. So any even power, x to the 6th, x to the 8th, x to the 12th, any even power is a perfect square. So that is a perfect square as well. So when I am factoring this, I know I'm going to get two binomials. The square root of 9x to the 4th would be 3x squared, because 3 times 3 would be 9, and x squared times x squared would be x to the 4th. The square root of 25 would be 5, and so I end up with 3x squared and 5, and then I'm going to want to make 1 the plus and 1 the minus. And so that is what I get when I factor 9x to the 4th minus 25. So again, here are some for you to practice. I want you to pause the video and I want you to factor these and then check your answers. So if you paused and you factored those out, again, you were looking for them to be perfect squares. All of these were perfect squares. We took the square roots and we made 1 a plus and 1 a minus. Now, when I got down here to number 4, I took the square roots and I made 1 a plus and 1 a minus, but what I ended up with was another difference of squares. This is a perfect square minus a perfect square. That means it can still factor again. Now, x squared plus 1 cannot. We said it doesn't work if it's plus perfect squares, but if it's minus perfect squares, it can. So I kept x squared plus 1 the same, but then I needed to take the square roots of these and make 1 a plus and 1 a minus. So to completely factor this one, I had to keep going until I factored it all the way.